Okay, in this question, we are told that A is a 4x4 symmetric matrix with eigenvalue decomposition A equals V lambda V inverse. What does that mean? As a refresher, the eigenvalue decomposition of a matrix is a decomposition of a diagonalizable matrix, which are the only type of matrix that you can do this for, into V lambda V inverse, where the columns of V, here we are told those are called V1, V2, V3, and V4, are the eigenvectors. I'll probably annotate that here. The columns of V are eigenvectors of A, and the diagonal entries in lambda contain, as you might guess, the eigenvalues of A. And they're sorted in the same order. So the first column of V, its eigenvalue is the first diagonal entry in lambda. The second column of V, called V2 here, its eigenvalue is the second diagonal entry in the diagonal matrix lambda. Okay. In addition to all of that, we're told that V, or the columns of V, are unit vectors as well. Okay, and in parts A and B, which I sort of think of as appearing as a pair of parts, we are given different possible values for this matrix lambda, and we are asked if V is an orthogonal matrix. What is an orthogonal matrix? An orthogonal matrix is one whose columns are all perpendicular to each other, or orthogonal to each other, and whose rows are all orthogonal to each other, and whose columns and rows are all unit vectors. Now, algebraically, an orthogonal matrix satisfies V transpose V equals VV transpose equals the identity matrix. Okay, usually we use the variable Q for an orthogonal matrix. Note that an orthogonal matrix must be square, which V, lambda, V inverse, and A all are here. Here, all four of these matrices are 4x4. Okay, or a non-square matrix can't be orthogonal. It can have orthogonal columns or orthonormal columns, but it can't satisfy this property. Here, remember, implicitly we're being told that the inverse of V is V transpose, and here we're also being told the same thing. V transpose is V's inverse, meaning you can multiply it V transpose on the right or on the left, and either way, it turns V back into the identity. Okay, and that's why for an orthogonal matrix, both the columns and rows must be orthogonal to each other, because V transpose V contains the dot products of all pairs of columns, and VV transpose contains the dot products of all pairs of rows. And if that dot product matrix in both cases is the identity, well, the identity contains the dot product of each, in V transpose V's case, columns with each other, and if those dot products of the columns with each other are 1, that means the columns are unit vectors, which is true regardless here because we were told that. And the off-diagonal elements are the dot products, in the case of V transpose V, of columns with other columns. And if those are all 0, well, that means columns that are not the same column are orthogonal to each other. By that I mean if you take any two columns that are different, they're orthogonal. Okay, that was a lot of information dumping here. What is the main idea? The main idea in this question revolves around the fact that we were told A is a symmetric matrix. Okay? And the key fact to remember about symmetric matrices is the spectral theorem. And the spectral theorem states, among other things, that when a matrix is symmetric, its eigenvectors for different eigenvalues are orthogonal to each other. You know, that's important enough. I'm going to write it here. Symmetric eigenvectors for different eigenvalues are guaranteed to be orthogonal. That's what the spectral theorem says. Let me clear up some space here. Okay? And so, keeping that in mind, let's look at part A. In part A, we're told that in A's eigenvalue decomposition, the lambda matrix on its diagonal has 4 different numbers, 4, 3, 2, and 1. What that means is these vectors, V1 through V4, which are the columns of V, which as I stated earlier are the eigenvectors of A, they all have to be orthogonal because V1 is an eigenvector of A corresponding to lambda equals 4, V2 is an eigenvector of A corresponding to lambda equals 3, and so on. But these are all different eigenvalues, and so these columns must be orthogonal to each other. That means V has to be an orthogonal matrix because V transpose V is the identity, but because V transpose is V's inverse, you can multiply it in either direction. So In this case, indeed, V is an orthogonal matrix. What's the situation in part B? The only difference is that instead of a 3 in this second diagonal entry, we have a 2. Okay, by the way, if it wasn't super clear, the zeros here just mean replace everything that is not on the diagonal with a 0. So there's lots of zeros here, not just one. But I wrote it that way for brevity. What's going on in this part? Well, we don't have 4 unique eigenvalues, right? The eigenvalue of 2 is being repeated here. And what that means is we don't know for sure if V2 is orthogonal to V3. What we do know for sure is V1 is orthogonal to this, this, and this. We know V2 is orthogonal to V1 and V4, and we know V4 is orthogonal to all 3 of them. Because from V4's perspective, all 3 of these other V's come from different eigenvalues. Okay, so it's orthogonal to all of them. But if you look at just V2 and V3, they might be orthogonal, but they might not be, right? If you think of it this way, if V has a dimension of 2 for its eigenspace, that is, it has 2 linearly independent eigenvectors, which it needs to in order to have an eigenvalue decomposition, because if it only had a dimension 1 of its eigenspace, but 2 repeated eigenvalues of 2, well, then it wouldn't be diagonalizable. Okay, it would have an algebraic multiplicity of 2, but a geometric multiplicity of 1 in this hypothetical situation, which means we couldn't diagonalize it. But since it is diagonalizable, the eigenspace for the eigenvalue of 2 here will be a 2-dimensional subspace of R4. So you can think of it as like a 2-dimensional plane. Now, which 2 vectors span that plane? Well, there are infinitely many pairs of 2 vectors that span that plane in R4. And the 2 that happen to be written down as V2 and V3 may or may not have been chosen to be orthogonal. Okay, if you imagine this as being a plane in R4, I could write down 2 vectors that are orthogonal here, like that one and that one. That's still in the plane here. Just imagine this is spanning my whole whiteboard. Or I could have written down that one and that one. They still span this same 2-dimensional subspace of R4, but they're not orthogonal in that case. So in part B, the answer is no. Now the spectral theorem, it doesn't guarantee that any time you diagonalize a symmetric matrix, the V matrix is orthogonal. It just says that when a matrix is symmetric, you can diagonalize it with an orthogonal V matrix. Now the way we usually state that for symmetric matrices is instead of using V, we use Q, which is the more commonly used variable for some orthogonal matrices. We say we diagonalize a symmetric matrix with Q lambda Q transpose, therein using the fact that the inverse of Q is its transpose if it is an orthogonal matrix, which is what I was talking about up here. Okay, so big idea. In part A, we had 4 distinct eigenvalues, so we knew the eigenvectors had to be orthogonal to each other, which made V an orthogonal matrix because the columns are unit vectors. And in part B, we had a repeated eigenvalue, which means because we are given the eigenvalue decomposition of a matrix into V lambda V inverse, it's still diagonalizable, but whether or not the V matrix is orthogonal depends on whether the corresponding eigenvectors were chosen to be orthogonal. They may or may not have been. So it's not, the no doesn't mean it is for sure not orthogonal. It just means we don't know that it is. It is not guaranteed that it is. Very well. Now, in the final 2 parts of the question, we are told to use the assumptions from the start of the question, but not anything specific about parts A and B. So instead, we are told that suppose X is some other vector in R4, which we can write as a linear combination of the eigenvectors of A. So it's 5v1 minus 3v2 minus 5v3 plus v4. And we're told for some positive integer k, a to the k times x is equal to, let me fill these in here, 40 v1 minus 81 v2 plus 0 v3, notice the v3 is missing, plus 64 v4. And the question is, what is the value of k? Well, what's going on here? The main idea here is that when you multiply x by a, you use the fact that v1, v2, v3, and v4 are eigenvalues to update the coefficients in this linear combination. Let me show you what I mean. Ignore this line for a second. Let's just start up here with x equals 5v1 and so on. AX is going to be A times 5v1 minus 3v2 minus 5v3 plus v4. The issue is, or not the issue, the opportunity is that I can distribute the multiplication by A. I can pull out the constant of 5. So here I have 5av1 minus 3av2 minus 5av3 plus av4. Okay, that was a little messy. av4. But because v1 is an eigenvector of A with eigenvalue lambda 1, I could write this as 5 lambda 1 v1 minus 3 lambda 2 v2 minus 5 lambda 3 v3 and lambda 4 v4. Now what would happen if I multiplied this entire equation, ax equals this stuff, by A once again? Well, I would just multiply this piece by A, this piece by A, this piece by A, and this piece by A again. And what that would happen is I would replace A v1 with lambda v1, but there's already a lambda here, so this would be lambda 1 squared. Similarly, this would become lambda 2 squared, lambda 3 squared, lambda 4 squared. So if I multiplied both sides of this final equation by A to the power of k, well then I'd have a power of k here. These would all have powers of k. And these would all have powers of k as well. And that's all we've done. So now, if I look here, I can match coefficients. So I have 5 lambda 1 to the k is equal to 40. Negative 3 lambda 2 to the k is negative 81. Negative 5 lambda 3 to the k is, well, that's going to be 0. Maybe I'll write what they equal down here. 40, negative 81, 0. And down here, lambda 4 to the k being 64. Now my question is, I need to find a value of k that makes all of these true at the same time. Okay? And in a question like this, we often pick the numbers to be relatively small so that you can work them out without a ton of arithmetic hassle. And the question is really just asking us to find the value of k, but it turns out for the most part we can find the values of the lambdas as well. There may be some ambiguity with the signs, but let's take a look. The easy lambda to figure out, first I'll say our goal is to find k, but then we can find the lambdas too. The easy lambda to figure out is 0, because 5 times lambda 3 to the k needs to be equal to 0, so the only thing lambda 3 could have been is 0. What's next? Here we have 5 times lambda 1 to the k needs to be 40. That means lambda 1 to the k needs to be 8. Let's write down some scratch work here. Lambda 2 to the k needs to be equal to, looks like 27. I'm getting that by doing negative 81 over negative 3. And then lambda 4 to the k needs to be 64. Now, what do you know about 8, 27, and 64? What there is to know about them is that they are all third powers. 8 is 2 cubed, 27 is 3 cubed, and 64 is 4 cubed. What that means is in all three of these cases, the eigenvalue, lambda 1, lambda 2, and lambda 4, well, and lambda 3, is being raised to the exponent 3, and so k is 3, and I can fill in what the lambdas were by saying this was 2, 3, and 4 down here. Why did I say something about sign ambiguity? Well, if this exponent was 4, well then, I don't know, if the eigenvalue was 2 or negative 2, in both cases, I would have ended up with lambda to the 4 being 16. So I don't necessarily know uniquely what the lambda would have been, but here, since I have an odd exponent, I'm good. So k is equal to 3, and this is what the lambdas would be. And then, to figure out k, I wasn't asked what the eigenvalues were, but I need to know what the eigenvalues were to answer the last part. Fill in the blank. As k gets bigger and bigger and bigger, or approaches infinity, what does a to the power of k times x approach? Well, a to the power of k times x the components of that vector, right? This is still a vector. The components of that vector are going to get bigger and bigger and bigger. They're going to explode to infinity, okay? But the direction of the vector, which is why the question only mentions the direction of the vector is described by the eigenvector with the biggest eigenvalue, okay? Biggest being largest in magnitude, okay? And that here is 4, but if this were -4, it would be the same answer, okay? The direction of a to the kx is always determined by the eigenvector whose eigenvalue had the biggest absolute value. So here, that's lambda 4 is the biggest eigenvalue. So the direction of this vector as k gets larger and larger approaches that of v4. And there's a nice visual of this in the notes if it's not immediately obvious why this is the case. To like rederive why this happens, we'd have to go through a bit more math than I think we have the time to do so here, but that's the main idea. Okay, let us know if you have any questions on it.